sketching polynomials with real zeros. So let's first discuss what a zero is. So a zero is going to be an input value to a function that makes the function equal 0. Now, polynomials can have more than one zero, and not all of the zeros are necessarily real numbers, but for the sake of this video and what we're trying to accomplish, which is ultimately sketching the polynomial, we're going to specifically deal with real zeros. Now, visually, real zeros are going to be our x-intercepts. So say I have some polynomial that looks something like this, and maybe I'll do a better sketch, something like this. We can see that our x-intercepts, we have 3 of them. And these 3 values are going to constitute our solutions to the function that make that equation equal to 0, and those are our real zeros for the polynomial. So what we're trying to accomplish, again, is to sketch a polynomial just given some function curve, and we're going to need to be able to identify 3 things. The first thing we want to find are the zeros themselves, which can be done through a factorization process that we'll see in a couple other examples later on in the video. But the second thing, once we have the zeros, we want to discuss what multiplicity means. So the multiplicity of a zero is the number of times the zero occurs in the solution set. And why this is important is it's going to dictate the behavior of the function at those zeros. So, for example, let's say I have this function f of x equals x plus 2 squared, and we want to find the zero. So we want to know, when does this equation equal 0? Well, x plus 2 squared can be written as x plus 2 multiplied together. And using that zero product property we've discussed before, for this equation to equal 0, either this term or this term has to equal 0. If they were both not 0, then the product of those 2 terms would not equal 0. So we set each one equal to 0, and when we solve them, we get x equals -2 in both cases. So our solution set is -2, but it appears twice. So therefore, this solution, we would say, has multiplicity 2, because it occurs 2 times. So if you were to solve a random polynomial and you get x equals 1, x equals 1, x equals 1, x equals 0, x equals 0, and x equals 3 as your 6 solutions, well, x equals 1 would have multiplicity 3 because it occurs 3 times. This would have multiplicity 2, and then 3 would have multiplicity 1. So you get the idea. It's just the number of times it occurs in the solution set. Now, what we want to pay attention to with the multiplicity is whether or not that multiplicity value is even or odd. So odd multiplicity versus even multiplicity. And I'll spell it out. Odd multiplicity is going to mean that the function is going to cross over the x-axis at that real 0. Even multiplicity means we're going to bounce off the x-axis at that real 0. Now, what's important to distinguish is this odd and even is in reference to the multiplicity value, not the real 0 itself. Then, once we've identified the multiplicity, the last thing we want is the end behavior. So quick review of end behavior. We have some polynomial p of x. The leading term will say ax to the n, and we have some other terms potentially. Remember, there's only 4 scenarios for polynomial end behavior. We could have an odd degree with a positive leading coefficient. We could have odd degree with a negative leading coefficient. We could have even degree with a positive leading coefficient, or we could have even degree with a negative leading coefficient. And we've done our infinity analysis. We're just trying to determine for that leading term, as x goes to positive or negative infinity, all the other terms become negligible. So that's why we only have to look at the leading term. But when we do that analysis, that'll dictate that the ends of the graphs are heading in specific directions. And when we analyze an odd positive scenario, we find the right end goes up, the left end goes down. And if we know the odd positive, we know the odd negative, we can think of that negative part multiplying by -1, and we know our transformation, so we're going to get a vertical reflection. Even positive, both ends will go up, and when we know the positive case, we know the negative case, so both ends will go down due to the reflection. Now, something to keep in mind here, as we've discussed before, odd, the ends of the graph will go in different directions, and even they will go in the same direction. So let's keep that in the back of our mind. And now that we have those three things that we need to worry about, let's jump into an example, see how it's used. So I have two functions here, f of x and g of x, and both of them are in factored forms. And when you have something in a factored form, identifying the zeros and multiplicities is easy. The end behavior, a little more complicated, but we'll get to that later. So for the sake of these two exercises, we're just going to identify what are the real zeros and what are the multiplicities. And then our last two examples, we'll put it all together for a sketch. So for f of x, we want to know when does this equation equal 0. So using the zero product property, either of those three terms needs to equal 0 for this function to equal 0. So x could equal 0, x plus 4 could equal 0, or x minus 1 could equal 0. Now you'll notice with the x minus 1, it's raised to the power of 4. As a reminder, that means x minus 1 multiplied together 4 times. Now I don't need to expand it out as long as I'm aware of that's what it means. And I don't need to write x minus 1 equals 0 4 times in total. So when I solve each of these, x equals 0 is already solved for us. That's one of our real zeros. When we solve this, we're going to get x equals -4, and this will get us x equals 1. So we have 3 real zeros that occurred as a result of that zero product property, but how many times did each zero occur in our solution set? So x equals 0 occurred once, so it has multiplicity 1. X equals -4 occurred once, so multiplicity 1. Now x equals 1 technically occurred 4 times. So again, I have to be aware of this exponent and what it means. So there's 4 of them. And when I solve each of those, I would get x equals 1 4 times. So we're going to have multiplicity 4. So you could write them all out, but just being aware of what the exponent tells you, the number of times it's being multiplied together when we have a whole number exponent, that can reveal its multiplicity as well. So we'll notice the exponent with the x was a 1 and the exponent with an x plus 4, although not present, again is a 1. So we'll see that the multiplicities correspond to the exponents for the terms we're using to solve to find our real zeros. So now let's do the same exercise with g. With g of x, we want to know when that equals 0. So using the zero product property, in order for that to happen, x squared plus 9 needs to equal 0, x minus 1 needs to equal 0, or x plus 2 needs to equal 0. Now before we solve, let's notice that the exponent of 1 here, so whatever I get from there, we should have multiplicity 1. We have a 5 and a 2. So whatever I get from solving x minus 1 equals 0 should have a multiplicity of 5 because it's occurring 5 times. And x plus 2 will reveal multiplicity 2 for that solution. Now this first one, quadratic equation that I have to solve, no middle term, so I can use square root property. We're going to get x squared equals -9, which is going to be x equals plus or minus 3i, because we're going to get a negative under the square root. Now this is an imaginary number, and there is no place to plot an imaginary number on a real number coordinate plane where both x and y axis are real number lines. So we're not going to consider this as a part of our solution set for real zeros. When we solve this, we're going to get x equals 1 and x equals -2. So in terms of real zeros, we found 1 and -2. And remember, 1 occurred 5 times, so it has multiplicity 5. And -2 occurred twice, so multiplicity 2. So we have all our multiplicities down. Now the number itself, all we care about is whether it's even or odd when we go to sketch our graph. So now let's jump into an actual example. We're going to sketch the whole thing from scratch. So when we're sketching a polynomial, the first thing we want to do is, well, let's find the actual real zeros. So I'll make note that we want real zeros. This is an unfactored form, so let's get it in a factored form. So f of x, we'll say we want to know when it equals 0, so I'll already set it equals 0. This has a GCF, so let's take out a 4x, and we're left with x squared plus x minus 6. Now that quadratic can be factored further, 4x, x plus 3, x minus 2. So this is its fully factored form, and once I have it fully factored, we can use zero product property, so 4x needs to equal 0, x plus 3 would need to equal 0, or x minus 2 would need to equal 0. Solving all of these will get us our solution set of x equals 0, negative 3, and 2. Now, once we find the real zeros, then we want to identify multiplicities. So we already know what the solutions are, 0, negative 3, and 2. Each of these zeros occurred one time, exponent 1, 1, and 1. So when we solved all of those, only occurring once, they all have multiplicity 1, and that is an odd number. So they all have odd multiplicity, which we'll need when we do our final sketch. And the last thing we need, so 3 things you need to identify: zeros, multiplicities, and then end behavior. The end behavior, we're looking at the leading coefficient. So leading term. The leading term is 4x to the third. We want to know what's going on as x goes to infinity and negative infinity. If you know your cases, this is a positive odd case. So the function, as we go to infinity, it's going to go to infinity, and as we go to negative infinity, it's going to go to negative infinity. So as we go to positive infinity on the x, remember that's moving right, and then negative infinity would be left, so that's your right and left end respectively. This end goes up, and this end goes down. So now we're ready to sketch. So we don't need much room. We're going to draw our xy coordinate plane. And the first thing I want you to do is plot the zeros. And we're going to mark off those zeros. I'll mark them off with red. So we have one at negative 3, 0, and 2. Once you draw in the real zeros, I want you to add in your end behavior next. And the way you do that is you go to your outermost zeros, so the one furthest to the right and furthest to the left. Because we don't know what's going on in between those zeros yet. We're going to have a rough idea in a second. But to draw in the end behavior, furthest to the right, we expect our graph to go up. The right end goes up, dictated by our end behavior, and that left end should go down. Now, what to do at the actual zeros is going to be dictated by our multiplicities. So with odd multiplicity at each zero, we expect to cross over. So when I cross over this first zero, I don't know how high it goes, and I don't know where it turns around. But again, this is just a rough sketch, so just go to a maximum, turn around, and then head to the next zero. At this next zero, it also had odd multiplicity, so I expect to cross over. Again, we don't know how low it goes or where it reaches its local minimum, so just turn around somewhere and head to the final zero. And I have no choice but to cross over, and I should feel good about that because I got an odd multiplicity for that final zero as well. So this is our rough sketch of the polynomial. You only need 3 things: real zeros, multiplicities, and end behavior. When you have those 3 things, you should be able to get a rough sketch. And let's do one final example, this time in a factored form. So the factoring has already been taken care of for us. So let's get our zeros. I won't go through the whole thing, but we should be able to see x equals 0, negative 4, and 1 are going to be our zeros. The multiplicities. How many times do the zeros occur? So 0 has multiplicity 1. Negative 4 has multiplicity 1. And then 1 has multiplicity 4. Because again, if we did that expansion out into a fully factored form without any exponents other than 1, we would see x minus 1 occurs 4 times. So when I solve that 4 times, I would get x equals 1 4 times. So let's make a note, odd multiplicity, because that's what we care about ultimately, odd, and then even multiplicity. Now this last thing, end behavior, this is where it gets a little tricky when you have a factored form. What you have to do is identify the term in each section that has the highest degree. So we have 3 sections, 2, 3. There's only one term here, so I'm going to take x. Now between x and 4, there's 2 things in this one, right? You always take the variable over the constant, get x. And then last one, between x and negative 1, we're going to take the x. And then you multiply them all together, but also consider the exponent associated with that term. So this final x is technically raised to the power of 4, that middle x is technically raised to the power of 1, and then that first x is technically raised to the power of 1. So you just identify the leading one, or the term of highest degree in each section, and then you multiply them all together, and we're going to get x to the 6th. That would be our leading term if we were to do the full expansion on this polynomial. So it saves you some time, because to identify the leading term otherwise, you would have to fully expand and multiply everything out. So only look at the terms of highest degree in each section, consider the exponents that they're technically being raised to, and then multiply it all together. So we're going to see we have a positive even scenario. So to save ourselves some time, we know that both ends would go up as x to the 6 being our leading term. So let's do our sketch. We're going to draw in our zeros. We know the end behavior is going to be drawn in after the real zeros. So furthest to the right, n goes up. Furthest to the left, n goes up. At -4, we have odd multiplicity, so I expect to cross over. I turn around somewhere and head to the middle zero, which also has odd multiplicity, so I cross over, turn around somewhere and head to the last zero. I have no choice but to bounce, and that bounce at 1 is supported by the fact that we have an even multiplicity. So I should feel good about this graph. So there's the rough sketch of this polynomial, given a factored form this time. So with a factored form, the real zeros and multiplicities are easy to identify. You got to do a little work to get the end behavior. But either way, that's how you sketch. So 3 things are necessary, and that's all there is to this video.